In this section, we'll discuss the motion of a spinning top. So here's our top. Recall we have a very simplified version of a top here where we just have a sort of a disc attached to a stem. The stem remains fixed at the origin for the coordinate system, so that's going to stay fixed there. We need to think about motion using the three Euler angles we discussed in the previous section. So one of the Euler angles we're interested in here is this angle, theta. So theta is going to be that angle between the stem and the z-axis. Another angle we need to worry about is the angle phi, and phi is going to be this angle between the x-axis and the projection of the center of the top on the xy plane. And then of course we have motion about the E3 axis. It's going to look like that, and that is the psi angle. So each of these angles will have some form of motion associated with it, and we need to keep track of all three. Now before we dive in to consider the Lagrangian form of the dynamical equations, as the book does in this section, let's think intuitively about what kinds of motions we expect to see for this top. So of course we have rotation about the E3 axis. That's going to be our psi motion, remember. And very often the tops are spinning very quickly about that axis as compared to the motions in any of the other two directions. Remember that our center of mass for a top is somewhere over here, and that means that gravity is going to pull like this on the top. It's going to exert a gravitational pull at the center of mass. And we've already seen that this gravitational pull results in a torque, which is, remember, R crossed into the weight of the top, and that gives us a torque into the page in this case. And so we expect that our top is going to precess around the z-axis, and that's going to be our phi motion. As we'll see, the top can also wobble up and down so that the angle theta here is going to oscillate. And this is a form of motion called nutation. And so we're going to have motion up, down and up along the theta direction. And each of these motions will have an associated kinetic energy. But only one of these coordinates, the theta coordinate, will actually have a potential energy associated with it. And of course the potential energy you can see here is going to be just related to the height of the top's center of mass above the xy plane. And the only coordinate, of course, that relates to that potential energy is going to be the theta coordinate. Psi and phi have nothing to do with the potential energy. And so as we'll see, we will get a conservation of the generalized momentum for the psi coordinate and for the phi coordinate. These will both be a constant because the Lagrangian, specifically the potential energy, will have no dependence upon psi or phi. But the theta momentum coordinate, that will not be a constant because the potential energy will have a theta dependence. And so let's see what those dynamical equations look like. Okay, so remember, returning to our Lagrangian formulation for the mechanics, the Lagrangian is the kinetic energy minus the potential energy. We saw the expression for the kinetic energy in the previous section. I'm going to skip to the written form. And so our kinetic energy consists of three terms. This term here has to do with kinetic energy associated with the phi dot. And there's an additional term down here associated with phi dot motion. There's a term here having to do with theta dot motion. So that's going to turn out to be the nutational motion that we'll see. And then finally there's a term down here having to do with motion along the psi direction. So this is our kinetic energy. And you can see that it's quite complicated, and there's a fair amount of dependence on the theta coordinate. So the theta coordinate actually factors into the kinetic energy So as we'll see, the theta coordinate factors not only into the potential energy, but also into the kinetic energy term. Now next, let's write the potential energy. This one's much simpler because we only need to think about the gravitational potential energy. So that's going to be the mass of the top, gravitational acceleration, r, the distance between the pivot point for the top and the center of mass, and then cosine theta. So that's our potential energy. So now let's write out our Lagrangian with these two terms. So with the kinetic energy and the potential energy. Okay, so here's our complete Lagrangian. We have our kinetic energies and our potential energy. Okay, first thing we want to do is apply the Euler-Lagrange equation. So remember, we have for the psi coordinate, time derivative of the psi dot partial derivative of the Lagrangian, that's going to be equal to partial Lagrangian with respect to psi. And in the Lagrangian, we see there's no dependence at all on the psi coordinate. Therefore, the psi dot partial of the Lagrangian, which remember is defined as the generalized momentum for psi, that's going to be a constant. And that's going to be equal to a fairly simple expression here. And that is a constant. Now, it's interesting to note that the generalized momentum for psi doesn't just depend on psi dot. It actually depends on phi dot as well. And this gets at this coupling between the different rotations that we described in class, because these different rotations for the Euler angles are not orthogonal rotations. You get mixing of the different coordinates. Okay, so now let's look at the phi coordinate, the Euler-Lagrange equation for the phi coordinate. Okay, I've rewritten the Lagrangian here for reference, and now we want to apply the Euler-Lagrange equation for the phi coordinate. Remember, we have this, and this is going to be equal to the phi partial of the Lagrangian. Well, again, there is no phi dependence on the Lagrangian, and this again is consistent with what we said right at the beginning, that psi and phi, since there's no explicit dependence of the potential energy for them, and they don't feed into the kinetic energies directly, their associated generalized momenta are conserved. Therefore, this quantity, which remember is the generalized momentum for phi, is a constant. That generalized momentum, now it's not a simple expression, and again this is because of this funny non-orthogonality of the different rotations. The generalized momentum for phi is this lengthy expression. And you can see here the advantage of using the Euler-Lagrange formulation. If we had to do this using Newtonian mechanics, this would be quite messy. But when we use Lagrangian mechanics, we don't actually have to worry about the individual forces. We just treat the energies and take their derivatives. Okay, and so this, along with the psi generalized momentum, those are both a constant. Now let's look at the theta coordinate. This one turns out to be more complicated because there's such a complicated dependence on theta throughout the Lagrangian. Okay, here again our Lagrangian, and now let's take the Euler-Lagrange equation one step at a time. We know first we're going to need the partial of the Lagrangian with respect to theta dot. Okay, so where do we have theta dot dependence? Right there. So there's only one place where theta dot comes in. So then the partial derivative of the Lagrange with respect to theta dot, that's just going to be lambda 1 theta dot. So that's not too bad. But remember, we need to now take a time derivative of this for our Euler-Lagrange equation. Again, that's not going to be too bad. Since the moments of inertia along the principal axes are constant, the time derivative of this is just going to be lambda 1 theta double dot. So that's not so bad. And then we also need to take the partial of the Lagrangian with respect to theta, and this is where things get quite messy. We can see that there's a lot of theta dependence. There's a theta dependence here, there's a theta dependence here, and there's a theta dependence here. Let me skip to the end and show you what the final partial derivative looks like. And so here's the Euler-Lagrange equation for theta in all its glory. We've got three terms on one side of the equation. So here's one term, and you can see that it involves both phi dot, so that's going to turn out to be the processional angular velocity, and then there's some dependence on theta itself. Second term here with a minus sign in front has a dependence on psi dot, so that's the spin about the E3 axis, and then there's dependence on phi dot as well as theta. And then we have this term right here, and that's the gravitational torque. And this is all equal to lambda 1 theta double dot. And so there's three different ways in principle that you could change theta double dot. You could have changes to psi, you could have changes to theta, you could have changes to psi, excuse me, this is changes to phi dot, changes to psi dot, and then changes to theta itself. Any one of these changes could actually induce an acceleration along the theta direction. Let's look at some specific simplifications for these equations to look at to gain some physical insight into the problem. Here's a particularly useful simplification for the dynamics of a top. Remember, we've got our spin about the E3 axis. We can have some precession in one direction or the other. That corresponds to phi dot. Spin about the E3 axis, that's psi dot. In many cases, we actually have the top starting out at an angle theta to the z-axis, and that angle doesn't actually change too much. And so as an initial simplification, let's imagine that theta is a constant, or at least roughly a constant. So that means that both theta dot and theta double dot, those are going to both be equal to 0. And what's going to happen is our top is going to precess around, turns out, at a constant rate. So phi dot will also turn out to be a constant. So we'll get a sort of a constant velocity of precession. But there'll be two different rates at which the precession can occur. And so let's go back to our Euler-Lagrange equation for phi dot and plug in this assumption that phi dot and phi double dot, excuse me, theta dot and theta double dot are both 0. Here's our generalized momentum for the psi coordinate. Remember, that's a constant. Well, if theta is also a constant, this means that psi dot is just going to be equal to some constant minus phi dot cos theta, which is going to be a constant since theta is a constant, over lambda 3. This constant here turns out to be the angular momentum about the E3 axis. And you can see that if you go back to the previous section 10.9. And so psi dot is going to turn out to be just the angular momentum about the E3 axis, phi dot cos theta lambda 3. And remember, of course, this angular momentum is going to be a constant. We just worked that out up here. So this gives us an expression for psi dot in terms of phi dot and then other constants. So let's take this expression here and plug it into our generalized momentum expression for phi. Okay, so here's our expression for the Euler-Lagrange equation for the phi coordinate. Now, all of this, remember, is equal to the generalized momentum for the phi coordinate. And as the book describes, this is actually the angular momentum for the top about the z-axis. As you can see that by going back to our diagram for the top and thinking about the motions that I described. And so this whole thing is actually just the angular momentum of the top about the z-axis. And that is a constant, according to the Euler-Lagrange equation. And so that means not only can we make a replacement Here, for this term, which we already saw was the angular momentum about the E3 axis, we can also call all of this equation another constant, Lz. And that actually gives us an expression for phi dot, the processional velocity for our top. So now we have lambda 1 phi dot sine squared theta plus this term here, which is the angular momentum about the E3 axis, cosine theta, equals the angular momentum about the z-axis. Now remember, for this simplification, we're assuming that theta is a constant, and then that gives us an exact expression for phi dot, our processional velocity. That's going to be whatever the angular momentum for the top is about the z-axis minus the projection of the angular momentum at the E3 axis on the z-axis, so there's that cosine theta there, divided through by moment of inertia lambda 1 times the sine of theta squared. And this is all a constant. And so what that tells us is that our processional velocity, our processional angular velocity, is a constant. And so let's take our processional angular velocity, which is a constant. We'll call that constant big omega. What we'd like to do is to apply the theta Euler-Lagrange equation to solve for that processional frequency. So remember, theta dot and theta double dot, those are both 0, and so equation 10.107, that's all equal to 0. And so we get this expression, lambda 1 omega squared, which remember that's phi dot squared, cos theta, minus lambda 3 omega 3 times big omega plus mg r, and that's got to be equal to 0. So this is an equation that's quadratic in big omega, and so what we're interested now in is in solving for the processional frequency. And so we have a quadratic equation for big omega, so we can apply, oops, wrong color, we can apply our quadratic equation. Here's what that looks like. So we get two roots, of course, is a plus and a minus. Lambda 3 omega, little omega 3, lambda 3 omega 3 squared. There's a square root here, and we divide everything by this. Now, very often, we're interested in a top which is spinning very rapidly, and we have this expression, this inequality, which applies that basically the angular momentum about the E3 axis is much greater than the angular momentum about the other axes, and so we get lambda 3 omega 3 is much, much greater than the other term inside the radical here. And so that allows a pretty nice little simplification. We'll still get two roots, but the expression can be a lot simpler. So let's look at how that looks. So here's our radical expression. Let's factor out the lambda 3 omega 3 squared term. So that brings this up here, omega 3, and now this is going to be times the square root of all of this. So we've got 4 lambda 1 cos theta mgr all over lambda 3 omega 3 squared, the square root. Now if lambda 3 omega 3 is big, then this whole second term is pretty small, and so we can Taylor expand this square root, and we get an expression that looks like this. So this square root here, 1/2, that's going to bring down a factor of 1/2, and then 1/2 times 4 is going to give us 2, and so we're just going to get 2 lambda 1 cos theta mg capital R over lambda 3 omega 3 squared. We can multiply the lambda 3 omega 3 through, and we get an expression that looks like this. So this is equal to 3 omega 3, excuse me, 3 minus 2 lambda 1 cos theta mgr over lambda 3 omega 3. Okay, and now remember that this is, there's a plus and a minus term here in our final quadratic equation, and so let's look at, when we plug this back in, what that all looks like. Okay, so here are our two roots, the approximate roots, when lambda 3 omega 3 is big. We see we get the plus minus here, and then we get a minus plus here because it had a minus sign in the previous expression. And so now we have two roots for the processional frequencies. There's two frequencies with which the top will process. The minus root, that's where this has a minus sign, and so it's going to cancel with that. For the minus sign, we get a minus sign, we get a plus sign here. And then we're going to divide all this thing through by this. And so the minus root for the processional frequency comes out to be mgr over lambda 3 omega 3. And you may recall that this is the processional frequency we got back in 10.6 when we looked at precession due to a weak torque. So the weak torque in this case, that's the torque due to gravity, and by weak torque what we mean is that the effective torque is small in comparison to the angular momentum here. So that's what we meant before. Now we see we've actually quantified this clearly. Let's look at the positive precessional frequency now. So we see that we're going to get a plus sign here, and in this term we get a minus sign here, and because we've assumed that this term is much bigger than this over here, then we're going to actually ignore this term. And so we're really just going to get these two added together, divided through by this, and what we find is the second precessional frequency is this, so that's the angular momentum about the E3 axis, the component of the angular momentum about the E3 axis, divided through by lambda 1 cos theta. And this, you may recall, is the free precessional frequency that we've seen in section 10.8. So we get the free precession in the case that the torque is small. And so these are the two precessional frequencies. We get one due to the torque from gravity, and then one which is due to no torque. So this is the free precession. So the top will actually precess due to both of these frequencies, due to both of these effects at the same time. Typically, one is much larger than the other, and so we'll see a lot more precession due to the free precession usually than due to the torque, which is weak. Now next, let's look at nutation. As I said, we will have motion along the theta direction. Here, of course, we've assumed that theta is a constant, which is a pretty good approximation, but it's not exactly true. And so let's look at what happens when theta is allowed to change. Now, although in principle you can solve the Euler-Lagrange equation for theta, you can solve that for the dynamics of theta. That turns out to be quite complicated and messy. The book proposes an alternative exploration of the theta motion by considering the total energy of the system. And remember, the total energy of the system is going to be the kinetic energy plus the potential energy, as opposed to the kinetic energy minus the potential energy, which you have for Lagrangian. Recall that the kinetic energy is quite a lengthy expression. I'll write it out here quickly. Okay, so here's the kinetic energy. Remember that we can write phi dot as, in terms of the angular momentum components along z and the E3 axis. So phi dot can be written as this. And this is true whether or not theta is a constant. So this expression holds even if theta is not constant. Likewise, we can replace this second expression here. We're going to replace that with the L3 component of the angular momentum vector. And the upshot of all this is that you can rewrite the total energy for the system as the term having to do with motion about theta plus a potential energy which includes both the gravitational potential energy and these two replacements that we've made here. So it turns into an effective potential energy. The effective potential energy expression is given by this expression here. So there's one term here, which is related to the phi dot motion, and then one term here related to the psi dot motion. And so these two terms here basically enforce conservation of the two angular momentum components that we require. So it's very similar to the conservation of angular momentum in the central force problem. In this case, though, we have conservation of angular momentum for two components. And then we, of course, have our gravitational potential energy. And so let's look at how theta will evolve subject to the constraint that the total energy of the system must remain conserved. Okay, so here's our total energy for the system. Here's that effective potential energy. And we see that there's some interesting behaviors. For example, this is a constant. So as theta changes, this doesn't actually change at all. So it doesn't actually contribute anything to the motion of the system. As theta gets larger, this term drops. So that term's going to get smaller and smaller as theta goes down. This is the term that actually says some of the more interesting behavior. We can see that if theta goes down, if theta gets smaller and smaller, as theta goes to 0, sine theta, that's going to approach 0. And so that means that this first term here is actually going to blow up as theta gets small. So the effective potential energy is going to go way up. Well, in order for the system to conserve total energy, that means that the velocity along the theta direction, that theta dot, has to go down. So as theta gets small, this term blows up. In order to conserve total energy, this term has to go down. So that means that theta dot will go to 0. In other words, as theta approaches some minimum value, theta dot will actually approach a smaller and smaller number, eventually to reach 0. On the other hand, if you have theta approaching its maximum value, pi, of course the sine of theta will likewise approach 0. And so that means that theta dot must, for the same reason, approach 0. And so the idea is that this effective potential keeps theta limited between two finite bounds. Very similar to other problems we've seen in the past where we have the potential energy climbing at either end of the coordinate axis. And so let's look at what a plot of the effective potential is going to look like. And so based on a discussion, here's the effective potential, and it's going to have this sort of funny, not quite U-shaped shape to it. For some finite value of the energy, E, the top will remain between two finite values of theta here and just about here, theta 1, theta 2, where the energy, where the effective potential reaches a maximum equal to the energy itself. And so we'll have our top essentially oscillating back and forth between these two finite values. This oscillation is called nutation. Nutation coming from a word meaning to nod frequently in Latin. So the top will appear to nod up and down. And so again, these are the three types of motion that a top will exhibit. The most obvious motion that you're most probably familiar with is motion around the E3 axis, so that's psi motion. Then there will often be, there usually is, a processional motion. That's motion around phi. So we've got psi motion, we've got phi motion, and then there'll be oscillations away from and toward the z-axis. That's the nutation. And so those are all the complex motions of a top.